Hello and welcome to Textbook Engineering Problem. Today we're working on Elementary Principles of Chemical Processes 3rd edition. We're doing problem number 3.13. The problem statement says, before a rotometer can be used to measure an unknown flow rate, a calibration curve of flow rate versus rotometer reading must be prepared. A calibration technique for liquids is illustrated below. A flow rate is set by adjusting the pump speed. The rotometer reading is recorded, and the effluent from the rotometer is collected in a graduated cylinder for a timed interval. The procedure is carried out twice for each of several pump settings. Assuming the liquid is water at 25 degrees Celsius, draw a calibration curve of mass flow rate versus rotometer reading R, and use it to estimate the mass flow rate of a water stream for which the rotometer reading is 5.3. Okay, so we're going to make a model with a couple parameters, and we're going to base that model on the data that they gave to us in the table. And so I'll go ahead and move over to the computer, and we'll input this table of data and then begin our data organization in order to calculate a mass flow rate model. Okay, so we've moved over to the computer here, and I've input the table of data that they gave to us here. They asked for a flow rate, a mass flow rate in kilograms per minute. So in order to do that, what we need to do first is get a volumetric flow rate based off of our volume and time data here, and then we'll convert that volumetric flow rate from volumetric flow into mass flow using the density. Okay, so the density of water at 25 degrees Celsius is about 1, and that's grams per centimeter cubed. Okay, so our V flow rate will be in centimeters cubed per minute, and that is the amount of volume that we collected divided by the amount of time it took to collect the sample. So that is our volumetric flow rate, and then our mass flow rate is the volumetric flow rate times the density. Our mass flow rate units will be in grams per minute, and then we can convert that to kilograms per minute, like it asked for. Okay, so we've got our grams per minute, which is equal to the volumetric flow rate times the density, which is 1. Okay, and then you have your kilograms flow rate, which is equal to that divided by 1,000. And now we've got our kilograms per minute for a given rheometer reading. So now we can make our model. So let's look at the data and see if it looks linear. See if we can use a linear model or if we need to adjust it so that it looks linear. Okay, so we need to make a data column. We'll do our x values, which are the rheometer reading, and our y values, which are the mass flow rate in kilograms per minute. Okay, that looks very linear. So let's go ahead and use a linear model, have a slope and an intercept, and these are our parameters. So we'll do slope is equal to our known y values divided by our known x value, or our, not divided by our known x values, but our known y values and known x values will calculate the slope, and then we'll do the same thing with the intercept. Our known y values and our known x values as inputs to this function, and now we have our slope, our slope and our intercept. Okay, so now we have our data here, so let's make a model and that's in kilograms per minute. Okay, and our model is equal to x times the slope plus the intercept. Okay. And then we'll add our model to the graph and have our x values and our y values. Okay. And then we'll say that there's no marker and that there's a black line here, so it's easier to see. Okay, so our model spans the same range, and it looks like the model fits the data pretty well as a linear model. So we've got a pretty good model here. It wanted us to model what is the value at 5.3 for R, and the value at 5.3 is 0.546 kilograms per minute. For part B, the mean difference between duplicates, DI bar, provides an estimate of the standard deviation of a single measurement, which was given the symbol SX on page 18 of chapter 2. Moreover, confidence limits on measured values can be estimated to a good approximation using the mean difference between duplicates. For example, if a single measurement of Y yields a value Y measured, then there is a 95% probability that the true value of Y falls within 95% confidence limits, where Y measured minus 1.74 times the mean difference between duplicates, plus or minus. For a measured flow rate of 610 grams per minute, estimate the 95% confidence limits on the true flow rate. Okay, so what they're asking is, given a measured value of 610 grams per minute, we need to put a confidence interval surrounding that measured value to say how confident we are that the true value of Y is within this range. So what we need is the average difference between duplicates. Okay, so basically that means that we look at these duplicate samples. So we've got a rheometer reading at 2, 4, 6, 8, and 10. We have duplicates at each of those values, and so we just need to take the difference between those duplicates, and then we need to average the difference. So let's go ahead and do that on the computer. So we've got our rheometer reading here, and then we've got our mass flow rate. They did theirs in grams per minute, so I'm just going to move grams per minute over here. And then they have a difference between the two. So this is R, and this is M flow. And then we'll do the difference between this one and the one right after it. And we'll drag that down and get rid of the extras here. Okay, so we're just looking at the difference between the duplicates. So you should only have 1, 2, 3, 4, 5 values. Okay, then we just take the average of these numbers, and that will give us the average difference between the duplicates. So that is our average between the duplicates. Now you'll notice that I chose a certain direction on this, and I said it's the first value that we took minus the second value that we took. However, you could very easily have done it the other direction, but I think it'll still give you the same confidence interval. Yeah, it'll still give you the same confidence interval. As far as the beginning part of this question where it talks about the standard deviation, I think you would just choose the difference that gives you the positive value, because the standard deviation is always positive. Okay, so but the confidence interval has a plus or minus sign, and so that plus or minus sign in the difference gets canceled out anyway. So we don't really need to worry about it for what they're asking in this problem. Okay, so we've got our DI value here. Okay, so now we just need to calculate our confidence interval. So we've got Y, they said was 610, and then we have our plus and our minus sign here. Okay, so our plus will equal 1.74 times this value, and our minus will equal it'll just equal the same thing, but negative of this. Okay, so the range, the upper limit is equal to this plus this, and the lower limit is equal to this plus this. Okay? We are 95% confident that the true value, not the measured value, but the true value, is between these numbers. It's not exactly 610. So 610 is not the true value, it's just the value that we measured. But we're 95% confident that the true value is pretty close to 610 and it falls within this interval. So that is it for problem number 3.13. Thanks for joining me, and I hope to see you in the next video. Be sure to leave any comments or corrections or anything like that in the comment section below. Thanks.